Welcome to Algebra 1, Unit 8, Lesson 7-6, Systems of Linear Inequalities. I work out of Pearson Algebra 1, copyright 2009. I'm Mr. Pilarski, and our objective today is I will be able to graph systems of linear inequalities. Example 1t, graph the system. Solve by graphing are the directions, and what we have to do is graph two inequalities over here. And effectively, what's going to happen, we're going to graph two straight lines that will intersect and form four sections. One section will not be shaded at all. Two of these sections are having a single shade, and the fourth section is our solution where the overlap occurs. So let's see how to build that and find the solution here. The first inequality is y is less than negative x plus 3. If you have any algebra background, you should know how to graph this by now, recognizing that this is in the form y is equal to mx plus b, which is the slope-intercept form. From this equation, we can find the slope and the y-intercept. I like to find the y-intercept first. The y-intercept is 3, which means it crosses the y-axis at 3. So that would be up 1, 2, 3. Now the slope of this line is equal to negative 1. Remember, if there's no number in front of a variable, the number's 1, and in this case it's a negative 1. Now what that means to us, slope is a ratio of the vertical change over the horizontal change, or the change in the y direction over the change in the x direction. In terms of a movement in graphing, from our y-intercept we're going to go down 1 and to the right 1. So from this point here, we're going to move down 1 and to the right 1. And from this point, we can go down 1 and to the right 1. And we can continue that pattern until we get to the end of the graph, or until you get the idea that it's a straight line right there. And since in this inequality there is no equal sign, the line is a dashed boundary. So from here, we go up, and that boundary is not a part of the solution. So if a point falls on that line, it doesn't make it true. So now we need to decide where to shade. We need to either shade above the line, or we need to shade below the line. And to do that, we can pick a test point. And the test point I always like to pick is 0, 0 if you can. You can see in the next equation, or next inequality, we're not going to be able to use 0, 0. Meaning we're going to put 0, 0 into this inequality. 0 is less than negative 1 times 0 plus 3. When we simplify the math on the right, we're left with 0 is less than negative 1 times 0 is 0, plus 3 is 3. So that gives us true. 0 is less than 3, which means this point 0, 0 is a solution. So we're going to shade effectively below this line. You can see I'm doing that blue, and I'm kind of doing it in a horizontal motion, filling that in a little bit so you get the idea. So now, when I go to graph this one, because this is the solution to this inequality, now we need to graph this inequality. I'm going to do that in red so you can differentiate it on the graph. And here, hopefully you recognize this is what we call a direct variation. If you're in my class, you definitely were taught a direct variation, and that's where the sum of the variable terms is 0. We can easily solve this for y by adding 2x to both sides. The 2x's on the left cancel, giving us 4y is greater than or equal to 2x. Then I divide both sides by 4. The 4's on the left divide out, leaving us y is greater than or equal to 1/2 x. Notice I didn't change that into a decimal. I just reduced the fraction 2 over 4 and wrote it in front of the variable instead of with the variable. So I have 1/2 x. So to graph this line, I know that it's going to go through the point 0, 0, because when x is equal to 0, y has to be equal to 0. So effectively the y-intercept here is 0. And the slope of this line is 1/2, 1 over 2, which means in terms of a movement, we're going to go up 1 and to the right 2. So from this point here, we're going to go up 1 and to the right 2. And here we can continue that pattern, up 1 to the right 2, to graph additional points. And we get the pattern there. And in this case, since there's an equal sign, we're going to use a solid line as our boundary line. And now we need to pick a test point, and we cannot pick the test point 0, 0. And the reason is this line goes through 0, 0. We already know it makes its solution, so we're going to pick another point. We're going to put the point x is 0, y is 1, so 0, comma 1, into this inequality, so negative 2 times 0 plus 4 times 1 has to be greater than or equal to 0, and of course it is. Negative 2 times 0 is 0. 4 times 1 is 4, and 0 plus 4 is 4, so that gives us 4 is greater than or equal to 0. So now watch when I shade here, I have to shade above the line. So above this whole red line, I'm going to shade red. And you can see that as I described at the beginning, two areas are going to be shaded singly. Down here, it's shaded blue. Up here, it's shaded red. Over here, one area is not shaded at all, and the fourth area is shaded twice. This, where it's shaded twice, I'm going to now darken in with a little bit of black. That's the actual solution. Any point in there would make both of these inequalities true, so that double shaded area. Sometimes you might see some students or teachers erase the non-shaded, or the where it's only shaded once, so you can really visualize the solution. That would definitely be a good way to do it, to erase out. So that would be the solution to this system of inequalities. Example 3T, we're going to be working with perimeter here in this perimeter problem. You need to make a fence for a dog run. The length of the run can be no more than 60 feet, and you have 136 feet of fencing that you can use. What are the possible dimensions of the dog run? To be able to solve this problem in an algebra class, you have to understand that this problem is talking about the perimeter formula of a rectangle. The first sentence here, or the second sentence, in the first part of the second sentence, the length of the run can be no more than 60 feet. We're going to write that down with the symbol L for the length, and that's a pretty sad looking L. Let's make that a little bit better. That the length is equal to, and it has to be less than or equal to 60 feet. It can be no longer than 60 feet, so the length has to be less than or equal to 60 feet. The second sentence talks to the perimeter, talks about the perimeter. You have 136 feet of fencing that you can use. You have 160 feet, 36 feet of fence to go all the way around. Now the perimeter formula is 2 times the length plus 2 times the width. In this case, the perimeter represented by 2 times the length plus 2 times the width has to be less than or equal to 136. So this system of inequalities is going to allow us to answer this question here. What are the possible dimensions of the dog run? When we graph and shade these, the region that ends up being double shaded is the solution, or all possible widths and lengths. So let's take a look at this. Graphing this one here, L is less than or equal to 60. Well, that's a pretty easy thing to do. This, depending on how we label our axis, and here we're going to label this L, and over here we're going to call this W. So if this is the length, 60 would be right here, right halfway between 56 and 64 is 60. So right here, I'm going to make a horizontal line, and it's going to be solid because it can be equal to 60 feet. So at 60 feet, I put a little line, a solid line, and it's going to be shaded below that. So I take the time to shade below that, and I, in essence, color below the line. Color shade in to indicate that down here is a solution, and notice I'm doing it in blue. everywhere below the line. And it's I get a little sloppy on the with the technology, but that's okay. So here in red, the perimeter formula, since it has the L and the W, what we're going to use is the 0, 0 method. And if L is equal to 0, what that leaves us with is 2W being less than or equal to 136. And when we solve that, divide each side by 2, W has to be less than or equal to 72. So when L is equal to 0, W is equal to 72, which is right here. We do the same thing then when W is equal to 0. In essence, this term goes away, leaving us 2L is less than or equal to 136. When we divide each side by 2, L is going to be less than or equal to 72. So here's the 72 here. So we have 2 points, so we'll connect them. In this case, again, it's going to be a solid line. In this case, I'll use red to connect these 2 points. And it's going to have to be less than that, so it's going to be below that line. We could pick a test point. There's really no need. So it's going to be everything below this red line. And you can see the shaded region, the double shaded region, is everything between the L axis and the W axis, this red line and this blue line. In fact, we could just erase this since it's such a small area. And over here, and really see the solution is everything below this line, and I didn't mean to erase there. Okay, but everything on that line and here in this double shaded region, any ordered pair would be a possible solution. In this case, W would be equal to 20 and the length would be equal to 36. So right there we'd have an ordered pair 20, 36. That would be one solution. Any of those would be a possible solution. So there's using linear inequalities to solve a perimeter problem. Example 4T. Here we have some real world problem solving. Suppose you have 2 jobs, babysitting that pays $5 per hour and sacking groceries that pay $6 per hour. You can work no more than 20 hours each week, but you need to earn at least $90 per week. How many hours can you work each job? Now what we have here is a part plus part is equal to whole relationship. And that part plus part equal whole relationship comes into play twice here. And I'm going to show you that. But first, let's think about this. What are the 2 parts in this problem? What is the whole? If we go back and think about what the whole is here, in this case, you can work no more than 20 hours. That's going to be real important for us. We can work no more than 20 hours. That's one of our wholes. So whatever we do, these 2 parts can't be any more than 20 hours. So these have to be less than or equal to 20. Now, what do I mean about these? The 2 parts. Now, what are the 2 parts that I'm talking about? The 2 parts are, in this problem, the fact that you have 2 jobs. The first job's babysitting, and the second job's sacking groceries. Another term for that would be bagging groceries. So if we pick variables that are meaningful in this case, so let's say B for bagging groceries or babysitting and G for sacking groceries, the number of hours sacking groceries plus the number of hours babysitting has to be less than or equal to 20, our whole. Now the other whole in this problem, where we get our other inequality, is the fact that we want to learn at least $90 per week. So in that 1 week's time, we want how much money we earn, $90, to be, and we want the sum of these to be greater than that. Now, what do I mean by the sum of these? Well, how much money do you make sacking groceries? You make $6 per hour. So that's going to become 6G. And the B, since you make $5 per hour, is going to become 5 times B. 6 times the number of hours you sack groceries for plus 5 times the number of hours you babysit for has to be greater than or equal to $90. So now we have 2 inequalities that we can graph. Now let me separate these inequalities. It's going to let me grab them real quick. Make them a little smaller now that hopefully you understand them. So we can work with them a little bit. Now these are real easy inequalities to graph, and the reason I say that, they're both in what's called standard form, and we can use the simple 0, 0 method. Now for this first inequality that I'm working with now, g plus b is less than or equal to 20. Well, that's going to depend on where we put our variables. And in this case, we can just put our b up here, making the vertical axis our b, and down here, g, the number of hours that we work with groceries, and over here, the number of hours we babysit. So if we use this simple 0, 0 method, if we say g is equal to 0, so we get rid of g, b is going to have to be equal to 20. So when we don't buy groceries, we're going to babysit for 20 hours. So that's our one ordered pair. Now the other ordered pair would be when b is equal to 0. When b is equal to 0, g would be equal to 20. So when b is equal to 0, g is equal to 20. Now that's a real easy one to graph. That's going to be a real easy one to graph. Now that's going to be a real easy one to graph because all we have to do is draw a solid line between these 2 points. It's an easy one-to-one relationship. And so that would be it. And that's our boundary line, and it has to be less than that. So we would shade in below that. Now, I'm not going to get real crazy with the shading here. You're going to see why in a minute. We're going to shade below that line. I'm going to color in a little more, but not too crazy. I'm going to end up erasing a lot of it. So let's graph the other inequality, this one here, 6g plus 5b is greater than or equal to 90. We're going to use that same 0, 0 method. I guess I'll use blue for that. If g is equal to 0, meaning we put 0 in for g, so 6 times 0 is 0, so what we're left with is 5b is greater than or equal to 90. And when I divide each side of that by 5, that gives me b greater than or equal to 5 goes into there one time with 4 left over. That'd be 18. So b has to be greater than or equal to 18, or when g is equal to 0, when g is equal to 0, b is equal to 18, which would be right there. And then the other end of that would be when b is equal to 0. We substitute that in, and we get 6g is greater than or equal to 90. And when we solve that, we get g has to be greater than or equal to 15. So when b is equal to 0, g is equal to 15, and it's going to be greater than that. So we're going to use a solid blue line there. And since it's going to be greater than that, we would shade above that line. The reason I said I wasn't going to get too crazy is we can see then where the actual solution's at. That's above the blue line. Should be getting in there closer, but where the actual overlap is between the two boundary lines. So that's the feasible region. That's where the solutions are going to come from, anywhere on the lines or in between the lines. So if we get rid of what's not the solution, I'm trying to be careful not to erase what is the solution. Just in between those lines. So any really point, any combination of hours, and we could even say in a decimal range, it really doesn't matter, but if we keep it whole, we could figure out that when you sack groceries for 10 hours, you could work for a total of babysitting for 9 hours and fulfill this requirement that you're going to make at least $90 and you're going to work no more than 20 hours a week. So anywhere on the lines or in between the lines would be an acceptable solution. How many hours can you work at each job? You have many, many different combinations that you could choose from.